Okay, so we are ready to start again. Welcome everyone to this month's ISFE webinar entitled Integrating New Digital Abilities into Design and Food Manufacturing through 3D Printing for Customized Nutritional and Sensorial Properties by Antonio Derossi and Rosella Caporizzi. Briefly, I'll introduce our today's speakers. Antonio is an associate professor at the University of Foggia in Italy, specializing in food manufacturing technologies. His work focuses mainly on additive manufacturing and robotics for creating sustainable, customized food products. He's associate editor for Future Food journal from Elsevier, and he also works as an external expert for the Horizon Europe research projects. Professor Derossi has chaired the Food Chemistry and Technology Conference and is also currently part of the scientific committee for the 2025 International Conference of Future Food to be happening in Singapore. He has authored more than 100 publications. He has 9 book chapters and over 20 invited talks. He has also received, has more than 3,000 citations with an H index of 31. Now about Dr. Rosella Caporizzi. She is a researcher at the University of Foggia, also in Italy, with a PhD in Management of Innovation in the agricultural and food systems of the Mediterranean region from 2018. Her research focuses on personalized food development through additive manufacturing technologies and the valorization of food byproducts using biotechnology. She teaches cereal-based foods, novel food products, and innovative ingredients. And Dr. Caporizzi is co-guest editor for the Future Food journal, and she's also editorial board and member for comprehensive review in food science and food safety. Before we start, please remember to mute your microphone during the presentation. If you have any questions through it, you can either write them on the chat so that you do not forget them. At the end, you can ask them directly to our speakers, or I can also read them aloud for you. Thank you for being here with us. And welcome, Professor Derossi and Dr. Rosella. It's a pleasure to have you as speakers. And now the audience is yours. Thank you so much.
Thank you. Thank you so much. Thank you for your kind invitation. It is very honor for us to be part of this series of seminar. Let me just a few seconds to share my screen. Yeah. I think now you can see my screen, right?
Yes, we can see.
Okay, so perfect. Again, thank you for your kind invitation. This is for us, for me, and for my colleague Rosella, a very good opportunity to connect with you and to share our main vision about the possibility to introduce emerging technologies in food system to increase the nutritional quality, the sensory quality, and also the sustainability of the food system. But today, we have more or less 1 hour to focus our attention on one most important technologies for us, that is the introduction of additive manufacturing in the food sector. So we decided to divide the next 45 minutes in 4 main chapters. First of all, very brief discussion and reminder about the challenges of food system and the needs of disruptive technologies. Then chapter 2, the main technical background, the definition of 3D food printing. Then chapter 3 will be dedicated to several applications from our lab and from the state of arts, just to understand the potential of this technology to enhance nutritional sensory properties, and also some important aspect about the safety of these technologies, the safety aspect. And then finally, a chapter 4 will be dedicated to future perspective. Essentially, there are many innovative way in which 3D food printing is moving, but probably we don't have time to discuss about all aspects. We will focus it on 4D printing, 4D food printing. So, okay, just a brief reminder about the sustainability of the food system. You well know that we have the Sustainable Development Goal of the United States, of the United Nations, with 17 sustainable development goal, and each of this contains several targets, several specific objectives. If I remember well, the total objectives, specific objectives are more than 135, but unfortunately, many of these are severely off track. Because if you can see this report, 2024 recent report from United States, you can see that only the 60% of these specific goal are on track. The 30% show only marginal progress. The 80% are in stagnation, and the 60%, the 70% are in regression. So this open a very important discussion. Which kind of technologies or strategies we can study, we can start to include, we can optimize, we can implement to face these challenges and to contribute in reaching the sustainable development goal in 5 years, because we have remaining 5 years till 2030. So if you can see from this infographic, this schematical representation, the European Commission introduced here the potential of 3D food printing. So this means that European Commission believe that this is a good, this technology show some interesting potential. But also, this report from FAO was published just yesterday, 44 emerging food innovation by 2050. We were lucky because our lab, our group was part of this, the group of experts, of international experts to create this report. That you can see that 3D printing is here. Also, this is the second report because the previous one, titled here, Plant-Based Food Product Precision Fermentation and 3D Food Printing. In this report, FAO focused attention on the food safety aspect regarding this innovative technology. But again, 3D food printing is considered one of the emerging technology. Of course, there is a lot of work to do, but there are some interesting potential and impact that later with my colleagues, Rosella, you will discover, and you will also, she will be able to explain better than me later. So, but now it is important to define 3D food printing, because probably many of you, or probably some of you, have at home a 3D printer for plastic material. So many of you know that it's possible to connect the digital world with the physical world. It is easy also in domestic condition to design a digital model of some objects, some items, and then to create a physical object, customized physical object with plastic material. There are several thermoplastic material that you can use in common 3D printing. But what about the definition of 3D food printing? We want to try to use this definition because we believe that is very precise and contain many important keywords. 3D food printing is a technology in which food design and manufacturing are strictly embedded, are infused in new digital ability and opportunity connected through and driven by data. So we have many keywords. First of all, 3D food printing is driven by data technologies. Second, there is the connection between the digital world and the physical world. That means that it is important also to co-create, because co-creation will be possible to co-create the shape and the internal structure that you want, also with some impact with, for instance, the texture properties. So there are many keywords here really interesting to better understand the potential of this technology. For instance, you can see in the video the movements that we designed. This is a basic food formula for biscuits, and you can obtain effectively what you want in terms of shape, in terms of internal structure. So now I want to show with you some of the most important technological background and the technological step. If you want to if you want to produce a 3D printed food, you have to perform 3 different steps. Pre-printing, before printing. That is a more or less, we can think that is easily mixing ingredients, but it is not so easy because it is necessary to obtain some specific technological performances. Then when you are capable to design and to prepare your printable food formula, you have to work with the digital part of the process, so digital design with CAD software, and then to optimize the printing condition. And finally, when you have in your hand the printed food, it is necessary, of course, post-processing to stabilize the food, for instance, baking, drying, freezing, frozen, and many other. But of course, the post-printing must be optimized to keep the structure that you have designed to obtain finally a good replica, a very high quality in the capability to replicate the digital design. So, okay, so the first step is the design and preparation of printable food formula. So the idea here, the basic principle here are mix different ingredients to meet specific nutritional content, but also to obtain printing performances, specific rheological properties that allow to deposit the material and to keep the structure that you have previously designed. You can see here from this very short video that sometimes you can have a lot of problem. For instance, in this case, many ingredients, and you can see now in few seconds that the viscosity of this food formula is not optimized, it is not good enough. And after some layer, the food material flow in any direction. So it is not possible to obtain a good replication of the digital design. Okay, but what about this rheological properties to optimize, and which kind of rheological property you need? We have to speak about technological properties before printing, resting state, during printing, and after printing, because before printing, it is better to have a viscosity, enough high viscosity to avoid the oozing through the nozzle. But during printing, what you want to obtain is a decrease of viscosity when you apply the mechanical stress to obtain a material that is easy to flow. Then, when you finish to print, as in this case, do you need that viscosity increase again to keep the structural properties, to keep the weight of overlying layers? So in this case, after printing, what we want to obtain is a solid after recovery stage, the increase of the viscosity when the mechanical stress ceases. Some of the most important rheological index are the yield stress, of course, because this is the minimum force to reduce the viscosity and to start the flow material, and also the viscosity during in printing. Of course, high viscosity is good for self-supporting material, but you can experience some clog, you can create some clog of the nozzle. When you have very low viscosity or medium low viscosity, of course, it's easy to deposit, but you can experience also the phase separation, because when you start to apply the pressure, sometimes happen that you have phase separation. At first, you observe the flow, the deposition of the liquid and then the solid part. And this is, of course, a wrong way to perform 3D food printing. In this topic, in this field, so the possibility to optimize the rheological properties, there are many papers published. Many authors used and tested different gelling material, like a different kind of a starch, for instance, in this case, native rice, gelatinized rice, or puffed rice, to better understand the change in terms of the viscosity and then the printability. For instance, you can see here with puffed rice 50%, the author experiences overflow. You are depositing too much material in comparison to the movement of the printer. Probably the best condition is this, a food formula with 25% of puffed rice. And here you can see a very high viscosity. That means an under extrusion. So you are depositing not enough material in comparison to the printing movement, the velocity of the movement of the printer. So viscosity is very important, and we have at disposal probably hundreds of papers. You can see here many papers that detail different result on the yield stress, mixing different kind of gelling material. For instance, and you can see also from the figures, sometimes they obtain good result or insufficient results. So then when you are in your hand a printable food material that is very different from a generally common food material, the second step is the digital design. So you have to work in front of your computer. You need some basic experience in digital design. You can see here from our previous work the possibility to digitalize biscuit with different void inside, and then to print this to obtain different mechanical properties. In this case, the main goal was to modify to design digital properties and to obtain different texture, to design something that can be used for instance, elderly people or teenager, or also different texture in terms of sensory preferences. You can use many digital software. For instance, we use a Tinkercad. It's very easy, also free of cost, but this is not for expert. There are many software for expert, for instance, Fusion, AutoCAD. There are many possibilities that you can use. This is not really a problem. You can open a free account at Tinkercad or many other software to create the external shape. This is also interesting because in general, if you download the first 50 or 100 paper in general, you can see very simple shape. Square, cylinder, triangles. Very few paper try to create inhomogeneous structure or very complex shape. For instance, you can see here again, star, hexagon, cube, cubes, cylinder again. Sometimes we have some more complex structure like this, squirrel, or also some artistic creators here. But in this case, very few paper tried to obtain and to replicate complex shape like this. So then when you have your digital model, now you have to translate the digital shape, the digital external shape in movement. And then you have to you have to define the printing movement and also the digital information that will drive the printer. So it is necessary to use a slicing software. Slicing software is essentially a software that slice your structure in many layers and then allow you to define the condition layer by the printing condition layer by layer. For instance, you can see here, this is uh, probably, okay, so yeah, started this video. You can see here that the slicing software allow you to observe before printing the movement of the printer and the deposition of the material. So you can change, for instance, the velocity, you can change many of variable to change also the internal structure. The slicing software and the optimization of the printing condition is very important because you can see in these three different examples. And the first one, probably A here, the printing is not good because probably you are depositing too much material in comparison to the rate of the movement, the velocity of the movement on this line. Here, the author showed the possibility to equilibrate, to balance the amount of material that you are depositing per unit of time and the printing movement. Here again, probably in this case is very easy to understand that is again unbalanced, but because you are, or the printing movement is so fast, or the amount of material that you are depositing is not in equilibrium with printing. So in this case, we are in under deposition here, we are in over deposition. And you can see the effect. The only structure that is very similar to the digital model is in this case. Okay, now I want to show you and discuss you the main printing variables that is possible to define on the slicing software. We have many variables. We have time just to see 4 or 5 most important, the very common and basic variable. One of these is, of course, the nozzle size. The nozzle size means the nozzle, the dimension of the tip, the nozzle that you can use. For instance, in this case, you can see in general, in the paper, in the state of art, in general, author used nozzle size between 1.5 millimeter and 0.8, 0.6. In very few cases, you can see experiment where it was used a very thin filament like 0.2, 0.4, of course, because the viscosity and the pressure that you have applied to extrude the material through a nozzle of 0.2 millimeter, it is very high. And so in some cases you have very big problem. So, but now you can see the differences here, nozzle size 0.2 millimeter, 0.5 millimeter, 0.9, 1.2. This is the estimation that you can see on when you use the slicing software. Of course, when you reduce the nozzle size, you are increasing the printing time because to cover all this surface, in this case, you need 28 minutes. The nozzle size affect the printing time. Again, a second very important variable is the layer rate. The layer rate is the distance between two layers. When you finish to print one layer, the printer moves in Z direction with a height of, in general, 0.2, 0.4, 0.6 millimeter. So it is really important to understand that in general, one can believe that you can use a layer rate that is equal to the nozzle size. For instance, with a nozzle size 0.1 millimeter, you can increase the layer rate of 1 millimeter. But this is not um, a good decision because in general it is a very good option to squeeze the filament to obtain a flat surface and then to increase the adhesion layer by layer. You can see that this is not possible in terms of food material. This case to print perfect cylinder is a wrong way. You have to print a flat material like here because you are increasing the structural stability of your food. Uh, of course, when you decrease the layer rate, you are increasing the quality and the resolution. You can see here, this is chocolate. This is a structure printed by chocolate with very thin layer rate, probably 0.2 millimeter. It is not possible to see the different layer. In this case, yes. So the smoothness of the surface, you can obtain a smooth surface decreasing the layer rate, but again, you are exponentially increasing the time to finish your structure, your food. You can see again here with 0.2 millimeter of layer rate, you need 47 minutes. This is the structure probably of one biscuit of a couple of centimeters. So in this case, layer rate of 1.2, you can finish in 9 minutes. Again, another two very important variable are in field level. So in field level is more or less the density, the 10%, 50%, 90%, and also the path of the movement. In this case, you can see here from here, it is the same in field level, but different movement, different path. This is not only important for the aesthetic shape, but this is important also for the structural stability and for the texture property later when you finish also after post-printing. Post-printing process, there are many options in general, common baking, innovative cooking. You can see here, for instance, the user of laser to cook layer by layer. This is a very innovative idea because you can gain the solidity of one layer and then to deposit another layer. Because when you have, for instance, 2 or 3 centimeters, the first layer on the bottom are squeezed and you can obtain a very significant damages of the original structure. In this case, some people are using laser to print, to cook at the same time of printing. Printing one layer, cook, printing one layer, cook, and go on. Now I want to show you something about, very briefly, something about the safety. For instance, one of the hot topic is if we can obtain, for instance, cross-contamination in our printer. And I want to show you just some experiment. There are only 2 experiments. For instance, in this case, with a commercial printer. Commercial printer in general have material that are commonly used in gastronomy, for instance, silicone, plastic. You can see here that the authors tried to understand the log reduction that is possible to obtain when you wash the capsule in 3 different positions of a washing machine with 2 different protocols, an EV protocol and a speed protocol. And then with different also food material, butter, sugar, protein, and other. I want to show you just some few example. For instance, let me take this. Okay, for instance, you can see here that with mixture of ingredients, you can see an high log reduction with the EV cycle and lower log reduction with the the speedy, but you don't have the same result when you change the material with butter or with protein or with sugar. This means that probably the viscosity, the addition of the food material to the cylinder in the decrease of change the ability to obtain log reduction, and of course with some impact on the safety. Again, if you clean in different position of your washing machine, you can obtain here, you can see here, very different log reduction. In this case, the mixer, in this case, these are position 1, position 2, position 3. Again, here, the EV protocols had showed the most important result in comparison to speed protocol. But there are some differences when you use a mixed food formula or just butter, protein, or sugar. Finally, what's happened about 40 days in refrigerator or 96 hours at room temperature? You can see here that, for instance, for 3D printed, the author observed a lower count of microorganisms for 3D printed material in comparison to the conventional one. In this case, psychrophilic total count, again, here in this case for 3D printed material, the author observed a higher viable count after 14 days in refrigerated condition. So this is we have very few information about the safety of 3D food printing material and also the shelf life. We also performed some experiment, but this is also an innovative aspect that is necessary to detail in the future. So now I want to ask Rosella, I want to stop my screen and to leave the stage Rosella to continue this seminar. Thank you so much.
Okay, thank you, Antonio. I will now share my screen. Okay. If you confirm that you can see my screen and clearly hear me, okay, thank you. I will continue this seminar discussing a bit the state of art in 3D food printing, highlighting some recent research applications and technological advancement in this field. As you can see in this image, the publications in this topic in 3D food printing increased significantly, especially in the last 4 or 5 years, revealing a growing interest of researchers, but also of industry in this technology in food applications. Here we reported the main key areas of research which covered specifically the capability to print several food material, how to modify this material to enhance printability and structural integrity, as Antonio showed us, it is so important to properly obtain specific rheological properties in 3D food printing, and an understanding on the effect of the printing variables on the final quality of the printed object. This slide illustrates the spectrum of material used in 3D food printing. Researchers have extensively tested traditional food material like chocolate, cereal, dough, vegetables, cheese, fruit, but given the growing interest in nutritional and sensorially personalized products, and also the need of a more sustainable food system, the use of uncommon sources of material like beeswax, microalgae, or new ingredients like food wastes were tested in the last years. But what about the main outcomes, the main impacts of this technology in the food system? First of all, 3D printing can be used. Additive manufacturing is a rapid prototyping technology, so can be used as a rapid prototyping tools to study and to analyze the properties of food products, reducing innovation time and costs. I will show you later one of our application in this specific aspect. Another potential economic and environmental benefit of 3D food printing is the reduction of the gap between the producer and consumers, which is the on-demand production. Furthermore, the co-creation approaches in which people would be directly involved in the digital design of their food products can be realized by 3D food printing, increasing potentially the liking for that food, and resulting also in a significant reduction of food waste at household maybe. But the most we think interesting aspect of 3D food printing is the possibility to create personalized food in terms of nutritional compounds, but also sensory properties. And we will see in detail this specific capability of 3D food printing. All these impacts are strictly related to some unique properties of this technology, which are mainly the capability to create any shape and internal structure, the possibility to precisely control the amount of food material during the deposition, during the printing process, but also the precise location of the ingredients or also taste compounds in the three-dimensional space. Specifically, for what regard the possibility to create new shapes and new internal structures, this unique capability can be used to control, for example, food texture. We can adjust, we can modulate the infill density, which is one printing variable, to create new food texture tailored for specific or different sensory preferences or also dietary needs. 3D food printing can make food also more engaging, especially for children or teenagers. For example, vegetables can be printed in playful design to increase acceptance among young consumers, encouraging their healthier eating habits. But also, another important sorry, another important application is for individuals with dysphagia or with swallowing difficulties, because we can create texture modified foods that are both safe to consume and visually appealing, improving the eating experience of these patients. 3D food printing also bridges the gap between food science, design, and culinary arts, allowing chefs, nutritionists, and technologists to collaborate on creating personalized foods, health-oriented foods, and also visually appealing foods, like reported in some of these images. For what regard the precise control of the amount of food material, we can design foods with specific shape, but also dimension. We can change the volume based on particular nutritional needs. We can adjust the infill density to precisely control the amount of food deposited, but also, as you saw in some of the videos, the printing steps allow the deposition of layers of material, and this is also another level of control of food deposited to create a three-dimensional structure. But a major advancement of this technology is the ability to control the spatial distribution of ingredients, taste compounds, and micronutrients. This unique property enables the creation of foods with customized flavor, for example, or with optimized nutrient delivery. I will show you one application on this aspect. And currently, researchers propose some strategy like the possibility to print multi-material, or also to create complex three-dimensional spatial configurations. I will now show you some of our experiments, how we contributed in these years to the advancement of this technology, taking advantage of the unique properties that we just discussed. Firstly, we explore the main principle at the core of 3D printing, which is rapid prototyping. So we produce some biscuits, modulating the shape, the internal morphology by varying some printing variables like the infill density and the infill path. Then we studied the dehydration kinetic during baking, and we demonstrated that the baking time required to achieve a target final moisture content significantly varied when we modulated the printing variables. So we can use this technology to study and to vary the dehydration kinetic of our biscuits. Also, in this table summarized the estimated acrylamide formation and the percentage reduction of all the printed samples toward the control. These results demonstrated that all the printed samples showed a significant reduction in acrylamide content when compared to the control. So these results support the importance and opportunity of using 3D food printing technology to generate food prototypes that could be used and tested to modulate the dehydration kinetic of baked products, to reduce, for instance, the baking time, energy consumption, the overall cost of production, and also the potential formation of toxic compounds like acrylamide. Then we studied, we used this technology to modulate the texture properties and the mastication work. I want to show you these experiments where we produced biscuits at low sugar content. We modulated the shape, the internal, the infill pet, and also the nozzle diameters. In this case, we studied the textural properties, but also the mastication behavior with electromyographic signals from the analysis of the masseter and the supraoid muscles. Okay, here we can see that, for example, for what regards, the texture, the samples with the larger nozzle diameter of 1.2 millimeters and with the 3 hexagonal path were the hardest one, and also influenced the mastication work, the masticatory muscles activity, and also the mastication duration. Also, results of sensory test demonstrated that biscuits with the thinnest nozzle diameter of 0.6 millimeter and with the gyroid infill pattern were perceived sweeter than all the other samples. And this is probably linked to the ease of fragmentation during the mastication work. So the sample which were less harder were easy to fragment in the mouth and were perceived sweeter than all the other samples. So these results show that 3D food architecture affects how food breakdowns in the mouth, leading to new sensory perception. Also, we examined whether innovation in the three-dimensional food structure could enhance satiation and satiety. To test this hypothesis, we created 4 different virtual models of varying textural properties and also of varying textural complexities. We studied, in this case, textural properties, which were significantly different among samples, especially in terms of hardness and crispness values. But more interesting results were observed with the satiation test. Firstly, we observed a significant effect of time after the satiation test, but specifically the hardest samples induced a higher sensation of fullness in the panelists and a lower hunger perception. This means that we can create new textural properties, new textural complexities with 3D food printing, inducing a higher satiety perception, thus decreasing probably the calorie intakes in some consumers groups. Also, I want to show you another example, a different approach to create personalized foods in a co-creation dimension. In this work, we printed some gummies. Here you can see the digital models, which was a simple cube with different internal voids, which differs in terms of their dimension, shape, and also location. We also created a virtual instrument. You can see here the front panel of the virtual instrument developed by using LabVIEW, in which anyone can introduce the macronutrient requirements, for example, vitamin D, calcium, iron, and this information is utilized as input data for generating the digital model. Then, while the dimension of the voids are estimated based on the individual requirements of micronutrients, the geometrical shape can be selected by the user, and these aspects are another co-creation dimension which can enhance the consumer acceptance, considering the overall effect of the visual aspect on the sensory perception. Here we reported some photographic and also microtomographic images of the printed gummies, also filled with a colored liquid inside the voids. And finally, I also want to show you another possibility where another study where we realized some model foods with a controlled release profile of functional compounds as a different approach to create personalized food with 3D food printing manufacturing technology. In this figure is reported the design of the model foods, which were created to deliver different duration of, in this case, we used riboflavin, so different duration of riboflavin release by varying the dimension of the inner structure. We demonstrated that it's possible to modulate the amount of micronutrient release during time, so to modulate the release duration during time through a proper design according to individual requirements. And given the unlimited flexibility of 3D food printing, we can change dimension, internal structure in different ways. So we can create this kind of model foods with controlled release profiles based on specific nutritional requirements of each consumers. Now, I want to briefly discuss some future possibilities, which is the 4D printing. While 3D food printing focuses on creating complex but static structures, 4D printing introduces a fourth dimension, which is the time. This means that printed food is designed to transform one property after the printing process is completed. This transformation can involve, for example, change in shape, in color, texture, or in flavor, or also nutritional content, all triggered by external stimuli, such as the temperature, pH, humidity, mechanical stress, etc. For example, this slide focuses on dynamic shape changes. In this case, researchers used a starch-based ink with varying concentration and applied some external stimuli like drying or mechanical stress, and they demonstrated that they controlled the deformation of these multi-layered structures. But also here we can observe how dynamic color changes can be achieved through a post-processing technique. In this case, applying an acid solution at varying concentration, we can induce color shift due to pH sensitive reaction. And also Lastly, dynamic nutritional changes highlight the potential for food to evolve nutritionally over time. And this is demonstrated in a project which is Edible Food Growth, where structures were printed with edible gels, spore-forming bacteria, and seed that continue to develop post-production. I want to conclude by briefly looking at the current landscape of 3D food printing in the market, because as reported in this document, the global market of 3D food printing products is projected to reach 1.9 million in the next 2 years. So these are some of the companies that currently produce 3D food products. For example, Nourished is a UK-based company that create some layered vitamin gummies tailored to individual health needs. In this case, the consumer can select for each layer the color, the taste, or the macronutrients to create their own gummies. Or also, this is Gastronology, it's a Dutch company that focused on texture modified foods designed for people with swallowing difficulties. Or this is Blue Rhapsody, an Italian startup that print pasta with traditional ingredients and with very complex and also in some cases customized shapes. And this is Open Meals, is a Japanese company known for its concept of pixelated 3D printed foods. They aim to digitalize the flavor, the texture, and the nutrients profile for futuristic dining experience. So in conclusion, the emerging world of 3D food printing is rapidly expanding because it offers transformative potential in how food is designed, is produced, and also is consumed. 3D food printing is not just about creating visually appealing food products, but it's about redefining the food supply chain because it offers a new solution for personalized food. It allows to reduce food waste, and it also enables the use of sustainable ingredients. So it opened and it can open in the future new possibility for food design, for texture modification, and also for functional food development. Here I also reported some interesting readings, some books on this technology in the food sector for those who are interested. So thank you for your attention, and thanks the group of the Emerging Technology and Food Formula Lab.
Thanks. Thank you both, Rosella and Antonio, for this interesting and very nice webinar. I'm afraid we only have time for just one question because we're running out of minutes. So anyone from the audience who would like to open the microphone and make one question or raise the hand? One. Professor Torres, just a couple of minutes, please.
Yeah. Yes, one question. Production time. So I'm thinking that everything took several minutes to be prepared. I mean, even thinking at home, it would be a challenge to feed a family with everybody asking different things to be produced. So, and then obviously in commercial production would be a challenge. What do you see there in the future?
Yeah, absolutely. For now, one of the most probably obstacle to scale up in industry as the time that we need to print some also small pieces. For instance, we need in general between 5 and 10 minutes to print one biscuit. So of course, this is a challenge, but from some example that Rosella showed, for instance, gastronology, they are capable to print hundred of pieces in between 1 and 2 hours. So we know that with the help of engineering, there are some company that were capable to obtain a 3D printer structure that is capable to accelerate close to be industrial level. Of course, it is not possible to compare 3D printing with extrusion cooking, but the help of engineering are growing, are allowing the possibility to print very fast.
Thanks so much. One last question. You can also write them in the chat if you don't feel brave enough. Okay, I have one last comment from Enrique. The samples in which you change the internal structure and evaluate texture, how far are they from an actual product, and how related are these properties to the ones we could expect on a final product, I think?
Rosella, if you want.
Yeah, I showed you some biscuits where we evaluated the texture. These are for us the final products. So the change in the internal structure are aimed to create new textural properties. So I don't know why Enrique expected the final products are different from what I show you.
I think it is after the post-processing.
Yeah.
Enrique, could you please clarify?
Yeah, I mean, if those samples were considered as the final product, then you have answered already my question. But yeah, I was thinking on other shapes, like external shapes. If you keep the same internal structure, but you change the macro shape, how we
Yeah,
can use this same data, or do you think for each change in external shape, do we need to characterize
no.
everything again?
Yeah. In some of our experiments, we produce, for example, a cube and an hexagon as an external shape with the same internal structure, and the textural properties are different. So also the external shape affects the textural properties, even if using the same internal structure. Yeah.
Yeah, thank you.
Thank you. Well, I'm really sorry that we need to cut everything to just keep on and respect Rosella and Antonio's time. But I'll save the questions that are in here and send them to you, or I don't know, Antonio and Rosella, if you shared your group and perhaps your emails. But
Yeah,
anyways,
absolutely. Yeah, sure.
Thank you both for this exciting talk. Thank you everybody for participating in it. Please keep tuned for our next webinar, perhaps the following month. And thank you everybody for being here. Again, thanks Rosella and Antonio.
Thank you so much
Thank
for your
you.
invitation. It was a pleasure.